In this video, I want to show a couple more examples of how we would find the area in polar curves. If this helps you, please like and subscribe for more math help. So just as a quick reminder, and I can put links to other videos at the end of this, but you should already know, hopefully have established that the area of a polar curve can be found by doing 1/2 the integral of the function squared r, typically how we write those, r equals. So let's begin by just shading which part of this curve, because I'm going to use this for a couple of examples, which part we're finding the area of. We're going to start by finding this area that I'm shading. Now, I always begin by putting a kind of a point at the origin. The reason for that is everything in polar coordinates starts at the origin. We measure angles off this, 0 radians right here. We measure everything as a distance away from that origin. Then I like to put a dot where the two curves intersect one another. And then we get rid of what I drew there. Then we draw a line from the origin to those intersection points. And what that really does is it helps to figure out which part of the curve is being drawn by the angles. And then it also helps to kind of see how we're kind of sweeping through the function. I always think about like a windshield washer or windshield wiper. Now, we need to know where those curves intersect, and the easiest way to do that is to just take those two curves and set them equal to each other, like this. So I would subtract 4 from both sides. I would divide both sides by 2. And then we're saying, well, we need to figure out where cosine is 1/2. Now, cosine is 1/2 at pi over 3 and 5 pi over 3. And if you are unsure of how to do that, I have a video that does a pretty quick kind of way to quickly do unit circle work, especially in the AP exam. I'll link that at the end of this. But for now, let's just kind of proceed through with pi over 3 and 5 pi over 3. Now, I'm going to write pi over 3 up here, which hopefully that makes sense, that that's the placement. Now, 5 pi over 3 down here, remember that in polar curves, you always must have your bounds go from smallest to biggest. This isn't like Cartesian or rectangular, X's and Y's, where if you accidentally reverse your bounds, it's not a big deal because you'll get the negative of the correct answer and you'll just switch the bounds. And in this case, actually having the bounds backwards will trace the wrong way around the circle. We always want to say going in the counterclockwise direction from smallest to biggest. So I want to write this angle in a different way, but get to that same spot. And the way to do that is with negative pi over 3. So instead of going 5 pi over 3 going around this way, instead I went pi over 3 in the negative direction this way. Okay, so let's begin. The farthest from the origin, that's how we measure here, rather than like the function that's highest up in terms of y, we measure furthest from the origin. That is the red function right here. So we began by doing 1/2 the integral of that function squared d theta. And again, the bounds are from negative pi over 3 to positive pi over 3. And let me just quickly kind of shade what I drew there. So that starts here and just goes out to that curve like this from the origin. Like I said, like a windshield wiper. And then I want to subtract out that other kind of wedge. So let me move that down where I have a little more room. So minus 1/2 the integral from negative pi over 3 to pi over 3 of this other curve squared. It's always 1/2 the integral of r squared. And then again, what that just did was this right here. And that would find us that area. Now, I would rely on my calculator to figure this out, and I can quick at the end of this video, I will make a quick example of how to use the calculator. Okay, let's do another area. Now let's say that we're doing this area instead. Let's shade this part right here. So again, I'm going to draw in those lines from the origin to the intersection point. And this time I'm going to write pi over 3 and 5 pi over 3. Same things. But the reason I can do that is because, remember, you always want to go smallest to biggest. It's got to go counterclockwise. So integrating from pi over 3 to 5 pi over 3 will give us the shaded part that we want. Now this time, the blue function is further from the origin. So we're going to start with that. We're going to have 1/2 the integral from pi over 3 to 5 pi over 3 of the blue function. And that, of course, gives us this starting up here and just shades all the way out to the blue, sweeps all the way through here till we tell it to stop. So then we want to subtract off that 1/2 integral from pi over 3 to 5 pi over 3 of the red function. Now, I should mention as I finish writing this that you can absolutely do this in other ways. You know, you could have integrated from negative 5 pi over 3 to positive or to negative pi over 3, negative 5 pi over 3 to negative pi over 3. You could have done pi over 3 down to pi and then just doubled your answer since it's symmetric. There are a lot of ways to do these, which is sometimes what makes them fun, but also what can make them a little bit easier. Actually, you have some different methods you can do this. Okay, so again, you would type this into your calculator and get the answer. Again, I'll show you one example of how I would do that at the end. Let's do the final area. The last area I wanted to focus on was this one, the area shared by those two curves. Now, I would start with exactly the same process of, put your point at the origin, put points at the two intersections, draw a line like this. Now, what is different about this area than the previous two examples we did is you'll notice that the lines that we drew, these kind of guidelines from the origin to the intersection, lie inside our shaded region. And here's what that tells me. The first region we did over here was bounded by those lines and completely outside of those lines. And therefore we found the area of the red and subtracted the area of the blue. The second region we found over here, again, bounded completely by those and outside of those guidelines. So we found the area of the blue and subtracted the area of the red. But now, instead, we have two regions. We have a region over here that is set by the blue between the guidelines, and we have another region set by the red and between those guidelines. This means we're going to find two areas and subtract them. Add them. So let me put in our angles again, pi over 3 and negative pi over 3. I'm also going to write 5 pi over 3 below it. So the first integral we would find, I'm going to start with the blue function. So the blue function, the circle, that sets the outside, or I sometimes think it's the perimeter, from negative pi over 3 to positive pi over 3. And the equation is 4, so 1/2 the integral r squared. Now let me just quickly shade in what we just did there. We started here, we just shaded out to the blue like this. Okay, and now we're going to do the red. So we're going to say 1/2. Again, we have to add these two together. The integral from pi over 3 to 5 pi over 3. Remember, the bounds have to go from smallest to biggest. They have to. Okay, and this curve was 3 plus 2 cosine theta squared d theta. And what we've done here is we started at pi over 3, and we just shaded to the red curve. One way to think about this as you sweep through is that the actual curve, again, sets the outside, the perimeter of your region. So this is the set of integrals that would do that. Now, a lot of times people will say, well, could you put the integrals together? Could you make it one integral? And in the first two examples, we could, because the bounds were the same. And as long as the bounds are the same and the coefficients are the same, you can put those integrals together. But you'll notice that in this particular example, we can't do that because the bounds are different. Let me quickly show you how we would type this one into the calculator, and I'll kind of rely on the fact that you can do the others. Okay, so if you're out on a blank screen, make sure first thing go to mode and make sure you are in polar mode. And then when you press the Y1, you'll see now you have R's instead of Y equals. And also when you type in, if I go down here, when you hit what used to be the X button, you'll get a theta. That'll automatically do that in that mode. So there's the graph. I already did a zoom square, so it looks kind of like the one we had before. And you'll notice again the circle, I'm going to integrate the circle from negative pi over 3 to pi over 3, and the other one from pi over 3 to 5 pi over 3 to get that area that they share. The way we type that in, my circle, notice, is in R2 and my other shape is in R1. I'm going to do 0.5 times, I press the math button right here. Math, number 9 is Fn int, so the integral. And we're going from negative pi divided by 3 to positive pi divided by 3. And then I don't like to type the curve in. I like to use the vars key right here. And if you remember, that was in R2. So I'm going to do R2 squared. That was my circle. So that should give me the area of the circle from negative pi over 3 to positive pi over 3. And then plus 0.5, math 9. And we went from pi over 3 to 5 pi over 3. And this was R. So vars go to polar. R1 squared d theta. And that way, once you've typed it in, you don't have to do it again. Hit enter. Oh, I forgot the d theta. Hit enter. And there's the area shared by those curves.